Okay, let's go. Today is also just going to be electromagnetism. We're going to continue with the electric field from yesterday. So let's just start with an example. So we had, not this guy, but we had, in this case, we have now an example electric field from two charges. So we have a charge here. I've done this stupid. A charge Q1, I have a charge Q2, and I have a R1 vector, which is just 0, A, 0, and I have a R2, which is just 0, and then it's of course minus A, and then 0, right? That is what we have, and we want to now, of course, write the electric field on the basis on these charges, right? Okay, so we need that relative vector. So R, our position vector, is going to be some coordinate of x, y, and z. So the first relative vector, R1, is of course just going to be x minus 0, so x, then y minus a, and then z. And then R2 is going to be nearly the same thing, but just with plus a, as you can see. Then what we can do is write the first component, not component, but the first part of that electric field. That's just E1. That's be on the basis of Q1. I have 4 pi epsilon 0. Then I have R1, not squared, but I need the magnitude of R1 cubed, right? We have the magnitude of R1 cubed. So this is just equal to still Q1 and 4 pi epsilon 0. And R1 is of course just x, y minus a, and then z, right? Like that. And then of course on the bottom now, we are going to have x squared, because it's the length, y minus a in parentheses squared, plus z squared, and since we have cubed, this will be 3 over 2, like that. Okay, and then for E2, we have essentially nearly the same thing, but we have the charge Q2. Then we have instead the relative vector R2. Then we have R2 cubed, like that. And then we have Q2 divided by 4 pi epsilon 0. And then we have x, y plus a, z. And then we have, of course, x squared plus y plus a squared plus z squared 3 over 2. And of course, the total contribution by the superposition principle is that we are just combining them. So nothing more. And if you write now the expression in there, you'll get the answer. It can't actually be simplified further, so we just keep it like that because it's a lot to write and I'm lazy. So that's it. Okay. But you will see that will be the correct answer. So you do the calculation here and just those two, and here it's still the same thing. You're just plugging that in. Okay. Now we want to visualize the electric field. So we are going to visualize the normal way with arrows, nothing special. We are going to have Q1. I can write that Q1, and that Q1 is minus 1 microcoulomb. So we need programming here. So I of course need to import not numbers, but numpy as np import matplotlib.pplot as plt. I should write a snippet for this. Import scipy. We need that constant.constants as sc. Okay, and then we had that a was in millimeters, so a is, what was it, 1e minus 3, of course, that's millimeter. And then what was the first vector? So q1, what was that I wanted? So q1, what was it? It was that the positive one? Q1 was minus 1 e to the minus 6 because it's micro. Then we have Q2, that's just plus, right? That should be plus, right? Q2, it's a positive coulomb, right? And then, of course, I can do below. That's just to make things a little more neat. So R1, and that was np.array, and it was a minus A0. Then of course R, we can have that like that. That should work. Okay, that should be possible. Perfect. So now we are off to a good start, and we want to visualize this field, or the field created by these two charges. You of course need that function. So we need R, like we had, R of I, Q of I, and we need the relative vector Ri, which is just R minus Ri. Then we need Ri normalized, and that normalized is just, of course, np.linearalgebra.normalize, and that's just Ri. Then we need to return, what was it? Qi, of course, divided by 4 pi. So np.pi, of course, that now we need a constant there. That's just epsilon 0. I need to multiply by Ri and divide by Ri norm cubed. Perfect. Okay. Now the usual approach, we need Lx, Ly, Nx, Ny. That should be equal to, what was, this field wasn't that strong, so it should be like maybe 2. Yeah, let's go with 2 and maybe have something like 20 points, right? That should be, so let's see, x is equal to np.linspace minus Lx and Lx and Nx. Just do it like that. Yes, yes, and yes, of course. Okay, then Rx, Ry is of course just np.meshgrid. X, comma y, we need that indexing, of course. Awesome. Now we have the indexing. I would now use vectorize, and the reason being is that we can't just pass in a whole grid and then just pass in R1 or R2. Oh shit, I need R2 there. Yeah, so you can't just pass a single vector and then have that grid. That wouldn't work. So I need actually to loop. You can flatten it, but I just loop it. That works. For I in range n of x, of course, and then for j in range for n of y. Yes, stop complaining. Let's see. Now we need the r vector. The r vector is, of course, just np.array and just rx at the position ij, and then ry at the position ij, right? That's our vector. If we go through the whole grid, that's just a position on that grid. And then we want the electric field for x, comma y. And this is just the same as saying E. We could have just stated that E, electric, for example, electric field is equal to, just to make this clear, I'm not going to do that. Normally I don't do it like this, but just to make it clear, it's fun. Electric field is, of course, the contribution. So we have E, we need R, and then we need the contribution from R1, Q1, and then we need to add that contribution, right? So we have E, and then I have R. I have R, yeah. I have R2 and then Q2, the contribution there. And then, of course, what we can do is state that EX, comma EY is equal to the electric field. So we just unpack that guy, and then we can say EX. Yeah, I need EX someplace. So EX is Rx.copy because it's the same dimensions, and EY. We don't need like that. That should be all right. We can just say plt dot. What did I do there? Did I import something stupid? No. Plt dot access and equal. I want that, and then I want plt dot quiver. We have Rx, we have Ry, and then we have of course the contribution E and EY. And just to make it a little more simpler, you can divide by A, because the vectors get a little bit crazy. So you can divide by A, and just to be a little bit clear. Maybe we can be cool. We can just say plt.x label and then dollar, and then I could say here rx divided by a, right? Right. Shouldn't that be no? Oh, x divided by a. So of course you moron. And y divided by a and plt.show. Yes, that should be very cool. No, that was not good at all. What is this? I think it looks like it's moving. So either I just stepped on something here or yeah. Oh, yeah. My stupid idea was actually stupid. I should have just done that. Oh, I could have done that, yeah. I know. That is what my mistake was, wasn't it? Now it should work. Yes. Okay, they are still pretty big, but it works. You can see that this is clearly this looks like electric field or magnetic field, like you can see, woo, and it goes back to that point, right? Okay, yeah, it's just that those arrows were a bit much, but it's all right. The solution is correct. If I play around with these values, maybe it gets better. You know, that maybe there's too many, now there's too few. Typical. Yeah, it was too many, now there's too few. Let's try something like 4. I think that's cool. Yeah, that was very cool. What are you doing? 4, 4, 5. Why was 4 so bad? It shouldn't be that bad. There was some calculation there that went very wrong. Let's 21 then. What? What's going on? Okay, the first, at least that worked. Why was it so bad? This is correct. So y -2 and 2, and it doesn't need any more than that. That's correct. Yeah, let's just stick with that. Okay. Maybe I keep and I do this instead. You get more vectors. No, not K. Yeah, that looks okay. That looks okay. Yeah. Okay, so the next part now is right. The strength of the field is by the size of the arrows. But as you can see, it works, but there's a better way of doing it. So what you could do, instead of passing in the actual vectors in Quiver, you can pass in the unit vectors. So let's say the unit vectors for e of x, so let's say n e of x. I of course need a magnitude, so e magnitude is of course just np dot square root. We can do the square root this time. Just ex squared plus ey squared, yes. And then nex is of course just ex divided by e. Why use email? And then ney and that magnitude. Now you can see that we have instead what we have now is of course instead of the vectors here, so I don't want to have that. Now I want the nex and then not this stupid thing here. I want ney. So these are just going to be unit vectors. And we can remove this. And we can set some scaling for them. Since the difference for them are so small, you should affect those differences more, and you do that by just using the logarithm. So I just use logarithm, and I can just use e magnitude, right, as my scaling. And then we need to set some CMAP, which is what color. I think plasma is one. That's cool. I think we can also have a color bar. I don't remember how to do that at all. That would be cool. Mappable. I have no idea how to use this, so yeah, just skip that color bar. But I think this works. Yeah, you can see. So it's very strong, the field here, and then it gets weak. And so this looks more like an electric or a magnetic field. Very cool. Okay. Very happy with that. That was good, and we're happy. And the next part we're going to do is that I'm just going to say some words on the lines. So there is also 2 other types of lines that I'm going to see is it tomorrow or on Friday? I remember it doesn't matter. But the next two types of visualization we can do are streamlines and field lines. Streamlines isn't used in electromagnetism. Why? Because they fit more they fit more for fluid systems, right? So in electromagnetism, what you usually have are some charges, right? You have some line going to this charge, then right this, like you saw in the image, right? Going from plus to minus here. And then if you instead had a lot of lines instead around those lines, many lines like that, that will be streamlines. Instead of having just one line that goes from one point to another and that has to be fixed, there's no cut there, that is our field lines. So we are going to focus on field lines. And the field lines are pretty easy. The tangent, the derivative, just represent the vector there, and that makes sense. If I had some particle and I drop that particle, I expect to follow this path, and that's either you could state it as the path of the tangents, right? Or you can state it as just placing that the particle is moving along each vector, right? So either the tangent or each vector. Pick and choose, right? So that is just the meaning of those lines there. And of course, that they can represent the closer they are to each other, the stronger they are, right? So if you have a lot of lines, like we saw the color, a little bit the same idea, right? If I had something like, not that color, but if I had this, of course it's strong. But if I had lines that are very close at some point, they can't cut each other, then that field is of course stronger there. That's just it. I'm going to tackle more of that tomorrow. Okay, now we can do some tasks instead. So these above tasks, all of them are boring. They're easy to do, so we're not going to do that. But this is where some of the fun starts. This actually answers one of my questions yesterday when I did that integral. So actually, I stated something. There was this surface, there was this flux integral. And actually, of course, I didn't think of it because it changed, or where that field went through was just a circle, right? And when it went to that flat surface, we in the next task change it to a hemisphere, and we still got the same answer. It's because the field still just went through that same surface here. That's what matters. If it's like this later, that doesn't matter. If the field, of course, is uniform, which it was. And the same idea is here, so you can use that same idea. So this, what I'm trying to say is that these two fields are pretty easy, right? But this field, instead of actually calculating that normal vector, you can just imagine projecting this down here, and then you can just use the length here instead. This one is of course shorter than this guy, but that will give you the correct answer. Because the flux, you can imagine that this is projected down, like this guy, and then you can see the field. That's the idea. So that's pretty easy. Okay, these two are pretty simple. It starts from -1 and goes to 1, so that's just 2. Same goes on this side, so that's just 2. You can write it mathematically. So we have that the flux, of course, is that surface integral. So the surface, and then our field was E is equal to E, and then of course in the z direction. So we had E like that, that was the surface, and ds. Now they was in the same direction, meaning that this will just be E0. Then we just have the surface integral, and then ds without the vector. So this is just the area, so the whole thing is just 4 times E0. That should be correct. And that's just 4 times E0, and if you just move this guy up, it's still the same, right? So it's just 4 times E0, right? And then you have this guy, like I said. This guy is tilted, but he's actually not the same size. If you project him onto the XY plane, he is actually the same size, so you should get the same answer. But what we can do, we can just do it more complicated. It's more fun. I want to do the more complicated stuff. Okay, so let's do it the more complicated way because 1, it's fun. 2, it's great practice. So those are just good things. Let's see. So I have this coordinate system. I just need to write this down. So we have X, Y, and Z. And it's just always a pickle to draw this. Let's see. Yeah, I should have done that like that. Okay. And then that X goes there, right. Okay, let's see if I can do this. You have that guy going, no, that was bad. Yeah, that guy going like this. Then he's tilted like that. That's okay. And then you have that line going like that. Then you have that line going like that. That's not too bad compared to the drawing in the image. That's not too bad. And at the end there, what do we have there? That's of course in the positive x and in the minus y. So the surface SC, positive x minus y and 0. So that just, I can do that in order. That just positive x minus y and 0. And the last one with 0 is of course negative all the way. So minus, minus, and 0. And then we have the one with heights. So the first one at that end, this point here, I'm going to change back. Let's see. This guy here, he's of course in positive both of them. So that should be 1, 1, yeah, 1 all the way there, right, for C. So that's just 1, 1, and 1. And that last guy is of course minus because we are minus x there, yeah. Okay. Cool, so this is my nice drawing. And of course, so if you want the normal, you of course just do the cross product. So let's say we had our vector there, that's v, and this is our vector u, like that, okay? And u is pretty easy. U is just, of course, minus 1, minus, so we get minus 1, that's 0. We get 1 minus minus 1, that's 2, and 0 and 0, that's 0. Correct? And then we, of course, get v, so vector v is, of course, 1 minus 1, that's 0. Then we get, is that correct? 1 minus minus 1. Do I get 2 again? Or did I write something? No, that's not correct. It's the first one that I missed. Minus 1, then minus 1. That's, of course, minus 2. Then I have 1. Then I have... No. Minus 1. Am I drunk? Am I drunk? What? Have I forgot how to do, like, subtract and add vectors? Yeah, okay, just write it like a moron. Minus 1, 1, 0, minus 1, minus 1, and 0. That's, of course, just minus 1, minus 1. That's minus 2. 1 minus minus 1. That's just 2. I can't remember that I had that the last time. That seems very weird. But let's just keep on rolling. Yeah. Okay. So v, that's just 1 minus 1. I should do that in my brain. Then I get 1 minus minus 1. That's 2. Then I get 1 minus 0. That's 1. Is this correct? This doesn't... 1 minus 1, 0, 1, minus minus 1, that's 2. 1 minus, yeah. Either I'm a complete moron or I don't know. It's alright, of course. But that normal vector is just u cross v. Right? And u cross v is just I hat j hat k hat, and then we got -2, 2, and 0, 0, 2, and 1. Like that. So I goes out, then you have just the right side. So you have I hat, then I get 2, and I get 0, so that's just 2. Yeah, that is correct. That should be correct. That sounds correct. Okay, minus j hat. I get -2. Yeah, just get -2 there, and 0. And then, of course, I have k hat. Am I today? Yeah, my brain is like, no. Plus k hat. Then I get -2 and 2. That's, of course, just -4. And 0. I think this is not correct. It can't be. 2, 2, and -4. I think I made some mistake. I don't know. How can I make a mistake with these vectors? I had 1. Let's see. I had 1 minus 1 on that v. That's 0. Then I had 1. Yeah, that's also just 1. Minus minus 1. That's 2. Right? I have 1 minus 0. That's, yeah. 0, 2, and 1. The first guy was -1. And then -1 minus 1. That's -2. I get 1. Minus minus 1, that's 2, and 0, and 0. Yeah, that should be correct. Okay, let's just move on. Okay, so that's the vector there, right? And the normal vector is just that divided by the normalization of that vector, right? So normalization of that vector is, of course, 4 and plus 16, so that's just 20. Oh, it's correct. It's actually correct. Very neat. So this n vector, and of course n hat is what we want. That's just 2, 2, -4, and that was just square root of 20, which is just 2 times the square root of 5, isn't it? Yeah, that's just correct. Cool. Now we can actually do this. So the integral is, of course, flux is, of course, the integral. And then we have E0. I can just put that one out over S. And we had 0, 0, and 1. And we need to multiply by, of course, 2, 2, and then -4. I think my projection is wrong here. I think I have it the opposite way, didn't I? Yeah, I took U cross V. It should be V cross U. You moron. So it's going to be the opposite, but that's all right. It should be 4. That's what we want. Yeah. I was like, what is this? Where did the minus come from? Okay. So that's that. And of course we have that was that, and then we just have the S, not vector, because we have written the vector. And of course I need to divide by 2 over square root of 5. Yeah. That should be very much correct. Okay. Now E0. Then we can move out. Let's see, we just get 4. So 4 E0. Now we have this integral here. And then ds, and then divided by 2 square root of 5. Now it turns out that this, what we looked at earlier, this is not the same size as those. Actually, the size here, I'm not going to do that, but the size of this guy is actually 2 times the square root of 5. So this goes away and we get the exact same answer. So very neat. A fun thing to do. And this should be the same answer. The other ones are pretty easy. This one is 0. And this one, again, if you use that same principle, if you project this onto here, this guy gives also the same answer. It has the same width as this guy and the same length here, so it will be the same solution. Yes. Perfect. Gradient. Okay. Find the gradients. Let's just do one of these, like this guy. Yeah. I'm not going to do them all. That's just way too boring. Okay, so V of R. V of R is just equal to x squared plus y squared plus z squared. That's just a scalar function, right? And we wanted that, the square root of that. Is that what we want? I want to find the gradient of this guy. That should be a vector. So the gradient of V, then of course what you have to do for each of the components, first 1/2 goes one below. So we have 1/2, right? And then the whole thing goes on the bottom. Y squared, right? And then you open up and you just get 2x. So 2 and 2 cancel out, and that's just x, and in the x hat direction. And you get the same for each of them. So you get y, x squared, y squared, z squared, 1/2, then y hat, and then etc. And what you can see is that what we have in common is 1/r, the length, right? But at the same time, what we also have are, of course, x hat, or x times x hat, I mean, x times x hat plus y times y hat. Oh my days, y times y hat plus then z times z hat, which is, of course, just, this is just r over r hat. No, r over the length, vector r over the length of r, and that's just, of course, r hat. So that's the answer. Perfect. Yeah, but I didn't write r hat, but that's all right. Okay. Divergence and curl. Let's do 2 tasks here. This one looks, I can just say 1, 0, 0, there's no divergence there, no curl here. This guy is certainly divergence, but there's no curl. This guy is, no, this is not going to be the 1, 1 and -2, so it's going to be 0 for both. This guy obviously has curl and 0 divergence, and this guy is one interesting. So let's do the interesting one. Then we can say we're done. Okay, so E is equal to the gradient of V0 e to the -y, and then sine x, right? First thing we should do is do something about, because doing divergence and curl on that is a little bit pain. So we can just open this up, and this is saying the gradient of this guy. Remember, the gradient is partial. This is a vector, so we are first going to partial in the y direction. So this is going to be v0. I can just place v0 out of everything. That's all right. So just v0 e to the -y. So we are just going to do the x part. The e to the -y stays. This is cosine of x, and this is in the x hat direction. Then we, of course, get minus because of that e. So you get minus, not y, but minus e to the -y. And then, of course, sine x. Very neat. Then we have that. And that's, of course, in the y hat direction. Don't forget that. Okay. Now we can do the divergence. So divergence is, of course, just equal to nabla dot e. That's just equal to each of the components in the x direction. You can just keep v0 outside. So you have e minus y cosine of x. If you do the cosine of x, that's of course just minus. So just minus e minus y sine of x. Then in the next part, remember this is a scaling of the vector. We have e minus y, so this in terms of y, they get plus. And we have e to the -y, still have sine x, and all of this is of course 0, as you can see. Then we do the curl. which is just nabla across the vector field. Just E there. We still have V0. So now I need to do the curl of this guy. Yeah, maybe I can. Yeah, I should have written that. You can write that curl there. So the curl is, of course, you just have 2 coordinates. Yeah, I'm so used to doing it like this, so I'm going to do it anyway. I, j, and k. Then there's, of course, partial, not too partial, on the basis of x, partial on the basis of y, and then partial on the basis of z, like that. All right, and then, of course, we have, I had e to the minus y cosine of x. We don't need v0, that's just in the way. Then we had minus e to the minus y, and then sine x. Sine x and then 0. Let me do it like that. Yes. That's just equal to I hat. Cross out this guy. Partial, that's 0. There's no z. This is just 0. Okay, minus j hat. J hat goes away. That's just 0. K, there's no z there. So that's just also 0. Now the question comes, is it a curl? So partial x in the x direction. We can do that. We do that, that's just minus e, and then of course to the minus y, cosine x. Then we get minus, then we have partial of this guy in terms of y, and that will just be the same. So we get plus. So all this goes out and it's equal to 0. Again, so no divergence and no curl on that guy. Yeah, that's correct. Awesome. Okay, perfect. Now we're finished for today, and I'll see you tomorrow.